Cool. All right, guys. Happy week 6. So this week we're gonna be talking about RNNs and LSTMs, so recurrent neural networks. Everything is in the chat, so you can find the feedback form plus the slides in the chat. So check that out. Yeah, let's get started. Also, reminder, we do have office hours right after this workshop at 9 o'clock. So you can catch us there as well. So cool. All right, let's begin. So today we're going to be talking about word embeddings, as well as a quick introduction to RNNs, what they do, how they work, as well as LSTMs. So yeah, it's going to be action-packed little workshop we got here. So strap in. All right, cool. Let's begin with word embeddings, which is sort of just a precursor, an introduction to um, how we how our data. One example of how data can be for RNNs. They might not be initially very related to RNNs, but once we begin talking a little bit more about them, you'll understand how word embeddings play into what we're talking about today. So yeah, so let's just take a quick look at these two sentences. So um, let's take a look at these questions first. So the baseball player can run over to catch blank, and the grizzly bear goes to the river to catch blank. So for us as humans, it's pretty easy to guess what words go in these blanks. So yeah, if you guys want to, you guys can put it in chat for a sanity check. What everyone thinks goes into these blanks, or feel free to unmute. I'll give you guys like 30 seconds because yeah, shouldn't be too hard. Yeah, the ball, the moose, sure. Um, catch these hands, yes. Grizzly bears do catch hands. Um, yeah. All right, cool. Yeah, so I'm seeing a few answers. And yeah, does make sense. So I guess for the first one, probably going to be the ball because it's a baseball player. That's like a first instinct. And the grizzly bear goes to the river to catch probably fish, salmon, something like that. Probably not hands, but it's okay. Definitely not COVID because I don't even know if bears can get COVID, but yeah. Um, so so let's try to understand why we knew what the answers for these fill in blanks were. Each sentence had a bit of context to it. So the first one, obviously the key words here were the baseball player and catch. And this kind of pushed us to think that the blank would be a ball. And then for the second sentence, we have the grizzly bear and the river. And um, these are also like keywords that we can kind of extrapolate from to realize that the blank is probably going to be fish. So we have a little bit of context in these sentences that helps us predict what the next word in the sentence is going to be. And that's easy for us to do. But what about for a computer? Well, computers are dumb, right? We need to tell them how to understand anything. They only understand um, one thing, and that's numbers, specifically ones and zeros. And everything we do on a computer is essentially an abstraction of these ones and zeros. Um, so if you want to, let the computer have any chance of recognizing what the next word in this sentence like this is going to be, we need to tell the computer every single other word in the sentence to give the computer context. Just as we have context when we read the sentence, we need to tell the computer that, hey, this is a sentence, understand the context, and then predict what the next word is going to be. So how do we How do we do that? We can't just feed in words directly. How do you feed in words to a computer? You need to convert these words into a form that is understandable by a computer. To So does anyone have any idea how we can do that? How can we convert words, letters into a form that um, that computers can understand? Um, Feel free to put it in chat what your thoughts are, or you can unmute yourself. Um, yeah, just a quick answer about how do you think words can be converted to understandable by computers. ASCII, yeah, that's ASCII is one example of how we encode letters so that they are understandable by computers. And at the lowest level, ASCII is just um, a uh, um, a byte, right? 8 bits that we use to encode numbers. A vector mapping of words. Yeah, exactly. So so everything here, gray, one hot. Yeah, perfect, exactly. So everything here, we realize that we need to convert these words into a number or a list of numbers to be represented so that the computer can understand what they are. Perfect. Um, so yeah. So these let's begin talking about how what word embeddings are and how these kind of fit into it. So before we do that, um, let's just say we need to convert words into some numerical form so that computers can understand them. That's the first thing we need to get out of the way as soon as possible. So let's just take a little bit of time to like define some keywords, or at least one keyword, which is vocabulary. It's going to come up a lot when we talk about word embeddings, but a vocabulary or vocabulary space, essentially all the set of possible input words that we want to give our model or we want to give our computer. Um, so how do we actually create these word embeddings from um, these just plain old words. Well, you guys gave some suggestions. We can use One Hot Encoding, which is something we're going to see in the future. I mean, not in the future, but like right now. And yeah, essentially a vector mapping of words, which is exactly what a word embedding is. It's just a way to encode words in a vector format in order to give it some amount of meaning. Um, so yeah, and yeah, when it comes to vocabulary space, we can create a vocabulary space from pretty much anything. You can take maybe the 1,000 most common words from maybe your favorite book, for example, and that's going to be your vocabulary space that you could feed into a model. And I think one super cool thing actually is, I don't know if anyone's heard of Zipf's law, ZIPF, but it's actually a pretty cool thing where you can choose like the few most commonly occurring words in a in like any sort of document, and it ends up you end up like selecting like the most occurrences of words or something. So you don't need to get like every single word in a book to like get all. I don't know. It's a cool little thing. Check it out if you guys want to. It's called Zipf's law, ZIPF. I thought it like related kind of well to what we're doing here with vocabulary spaces. Okay, I see a few questions in chat. Um, is this how autofill works? Yeah, so we're going to talk about this actually. Um, this is the precursor to autofill. So if you think about it, autofill is it's looking at what you're typing in, right? It's understanding the context of that sentence you're typing in, and then suggesting words that it can potentially be, which is what we're going to be talking about in this workshop, NLP, natural language processing. But word embeddings is a step back from this. We're trying to understand how can we even begin considering the process of autofill. How do we even make computers understand what words are? And that's what we're going to be talking about in word embeddings. All right. How do you decide what attributes should be matched within the vectors. Okay, so I'm not too sure what you mean by
Sorry, that was
attributes.
a little unclear, but like, so when you're deciding like which vectors are closest to each other, um, when you're comparing two like completely unrelated words, like how would woman compared to and versus like woman compared to like to or something? Like how do you decide which of those are closer to each other with the vector?
Okay, all right. Yeah, hold on to that thought because that's exactly what we're going to be, that's exactly what you're going to know by the end of this entire section.
Okay.
And we're going to be getting into this. So yeah, hold on to that thought.
Okay, thank you.
Um, mhm. Is Vertex a library? No, it's actually a neural network. It's a model. It's a fully connected neural network that we use to actually create these word embeddings. And we're going to see how we actually create these word embeddings with Vertex. Um, so yeah, um, cool. Yeah, let's move on. So um, let's begin really simple, and let's take a naive approach to how we can create, how we can encode words, and that is one hot encoding. So you can, it's pretty understandable from what you can see here. Let's say if you have a vocabulary about 100 words, you're essentially, each word is actually going to be a vector of length 100, and each word will have a corresponding index for which it has a 1 in, and all other entries are 0. So you can see here Rome is assigned index 0, and that value for the vector for Rome is 1, everything else is 0. Paris is assigned index 1, so Paris's um, index 1 value is going to be 1, everything else zeros. Italy is index 2, France is index 3, and so on. Um, but let's think about this. Is this actually a good way of creating word embedding? Is this a good way to encode words? Why? There are two main reasons why this is not the best way to go about it. Can anyone like um, say why? Unmute yourselves or just put it in chat. Why do you guys think this is not the best way to go about encoding words? It's large, yeah. Lots of zeros. Very memory intensive. Yeah. Since we this would be inefficient. Yeah, perfect. Amazing. Yeah. So that's one. Yeah, the first thing is this is very computationally intensive. We're using a lot of memory here. And the issue here is we want our vectors whenever we're talking about, especially when we've done work with models in the past like CNNs, and all like neural networks, all that sort of stuff. We want data that is dense and rich with information. Like CNNs, for example, we start off with this non-dense input of these images, but as we pass them through all these convolutional layers, like the vectors that make up the entirety of our model, all this data becomes so dense, so rich with information because we're identifying these features, and all these like high level and low level features that essentially lets our like feed forward neural network at the end of all these convolutional layers to easily identify and classify what these pictures are. So we're taking all this data and we're making it super rich with information. But here that's not really the case. You have all these zeros and you have these ones like here, like in some places, and it's not very rich. It doesn't tell us much. It can identify each word uniquely, but that's about it. It's very sparse information, and we want data to be rich with information when we're dealing with um, neural networks and all these computationally intensive models. Um, okay, cool. Let me see. There's a few more things in chat. Doesn't capture relation between words. Probably between a word is 0. Um, yeah, yeah. Exactly. Perfect. And yeah, that's the next big thing. Um, one next slide actually. So yeah, all these words are one hot encoded, and because of that, they have no relationship to each other whatsoever. Like every single word has the exact same relationship to the other word because they're all essentially orthogonal to one another. And when I say orthogonal, I mean like if these were vectors, they would all be like at 90 degrees to one another. So calculating the dot product between these vectors, because we can calculate the dot product between two different vectors to understand the relationship between these two vectors. And since all these words are essentially vectors, calculating the dot product when we use one hot encoding, as you can see here, will always result in 0. That means every single word, the relationship between every single word is 0. All words have the same relationship to one another. That makes no sense. That's not how we think when we assign context to words. Some words are related to others more than others. So because of that, one-hot encoding is one way to encode words, just not the most useful. Um, so, so yeah, because of that, we have no relationship to one another. Yeah, words have no relationship to each other. And this sort of picture here, this 2D space, it kind of shows you how we want to map our words into this sort of 2D space that effectively shows relationships between words. You can see here in this picture, for example, man and woman are close to each other because they encode for gender. King and queen, royalty, they're close to each other. Man and king, um, again, related to one another, obviously. Um, so all these words that are related to each other, they're closer together in some sense. So when you calculate the dot product between the vectors that encode each word, we get some value that tells us how related these two words are. But with one hot encoding, we don't get that. Um, and that's problematic. If you think about it way back in the context of the first sentence we talked about with the grizzly bear and the river and the catching, if all the words have the same relationship to each other, how would it tell us what the next word could ever be, right? Because the computer would have no clue because all the words to it at least would have the exact same relationship. So yeah, um, not the most useful. But yeah, we're gonna move forward and we're gonna see a few better ways of doing this. So yeah, this is where word2vec comes in. Um, so word2vec is a fully connected neural feed-forward neural network. So think back to week 1, essentially. Um, yeah. So it's just a plain old neural network. You guys know what it is. But it is very useful because it will give us word embeddings. If we pass the word2vec architecture, the word2vec model of vocabulary space, it will give us word embedding for each word that gives us context between these words in the vocabulary space. And that is what we want. We want context in our vectors. So yeah, word2vec comes in two different flavors, you could say. Continuous bag of words, we'll call it CBOW, and skipgram. Um, and we're going to take a quick look at each one. We don't have to like get very much into them. We just need to understand how they work at a high level. So yeah, so CBOW. Um, so let's go back to our first initial example of this sentence. The grizzly bear goes to the river to catch fish. So a sentence like this will be part of essentially the training data for our like word2vec CBOW model. Um, these are sentences that make up our training data. These are the sentences that give context to the words. So all the words in this sentence gives context to fish. And in the exact same way, fish also gives context to every single other word in this sentence. So the way CBOW works, right, is um, you have this feed-forward neural network as we discussed over here, and as you can see, the input layer here actually takes up all the words in this sentence except for fish. So we're talking about every single word that we know in the sentence. And we want this model to predict what this next word is going to be. All right. And that is the output here, a single prediction of what this next word is. This projection here in the middle is essentially a hidden layer. And we don't know how many neurons in the hidden layer, that would be a hyperparameter that we can choose. And that would tell us how big our word embedding is going to be, at least in terms of the length of the vector. So yeah, the way this works is you have all these inputs, which are all the words in the sentence. Essentially, the grizzly bear goes into the river to catch, and just that, not fish. We pass in all of that as our to our model, our CBAO model. And then we have this hidden layer, a lot of weights going on, all that sort of stuff. And then finally, the CBAO model predicts what the next word could be. And sometimes it'll be right and sometimes it'll be wrong. So maybe the first time you train it, it's going to be wrong. It's going to be way off. But the thing is, we know what the next sentence, what the next word is going to be. We know it wants to be. We need it to be fish. This is part of our training data. So if the output is, for example, say candy, we can tell the model, hey, that's not what we want. We can calculate an error, right? Because we have our expected value, which is fish. We have the error. We have the actual prediction, which is candy. We calculate an error from that, and then we backpropagate. Just a good old fashioned backpropagation. And this essentially trains all the weights in this model. And then eventually, by after we train over multiple epochs, we can finally fine-tune the output to be the word fish. And when we do that, if you think about it intuitively, we're passing on this input, which are all these words in this sentence, and our final output is fish. So essentially what we're doing is we're creating this sort of relationship between all these words in the sentence and the word fish. So now we have all these values, all these weights that we've trained, and all these weights that we've trained hold some relationship that is a numerical value that defines this relationship between the word fish and all the other words in the sentence. And all these weights that we train is what our word embedding is. So yeah. Okay, I see a lot of things going on in chat. I wanna be a part of this. How would you quantify the error? Okay. How would you quantify the error? There are different ways of quantifying the error. We're going to say again, as I said, these CBAO and the other model we're going to talk about, we're just going to understand high level skipgram. CBAO and skipgram, we're only going to understand these at a high level. So we're not going to worry too much about the intricate details here, because these themselves are their own neural network models and would need their own sort of discussion. We're just talking about them at a very high level here. So there are different ways to quantify the error. You can definitely look them up. So yeah, how closely related the output is to fish. Okay, yeah. Let's see. Okay, all right. So this is so the output is not going to be one hot encoding. The input is going to be one hot encoding for each of these. Each of these values are going to give in. Okay, so a bit of context, I guess. When we pass in these values into our input, we've already defined a one hot encoded vector for each word in our vocabulary space. That's where we begin. That's our starting point. All right, and then we pass in these one hot encoded vectors into the CBAO model, and we eventually and then we spit out the expected word that we want for the sentence. And then the weights that we've trained and learned through this model represents the word embedding for that outputted word. Let's see. Yeah. Yeah. All right. Perfect. Cool. Let's see. Okay. See, if this is confusing at first, realize that this is its own neural network. It requires its own amount of studying. We just need to talk about it super quick so you guys can understand how it works at a high level. So essentially what you need to take away from this, guys, is CBOW takes a bunch of one hot encoded vectors in as input. And then these are all fed into this neural network, which has all these weights that we need to train. We get an output, which is a word, and then we figure out if this word is correct or not. If that is that the expected output. We backpropagate. We train the weights. We train our weights, and once we get the expected output, those weights that we've trained becomes the word embedding for this output, for that output word, which in this case is fish. Do we import CBOW? What do you mean by import? Yeah, could you just clarify that for me?
So like from a library, or so if we want to use this neural network, right, either we train it first or we import it from somewhere so that it's already trained.
Okay, yeah. I'm not too sure. I haven't really worked with CBOW before, but I would assume that it is something that's already defined for us to work with. So yeah, I would assume it would be something that you can import, but I'm not too sure about that. So yeah.
Yeah, just to make a quick note, right? So you can either import it as a library function and pass in the words you want to be in your vocabulary, or you can go online and find the word embeddings that someone else came up with. So it would work both ways.
Got it. Thank you.
Yeah. Perfect. So the weights would only work specifically with this sentence. Exactly. Yeah, because we're only passing in the words in this sentence, as well as I guess every other sentence that uses the word fish. Because all we want to do here is we want to take this word fish, find out everywhere it's occurring in our vocabulary space. So if we're taking our vocabulary space as like a book, for example, we have all these sentences in a book. We can just find out all the places where the word fish exists in that sentence, take all those words from the sentence, chuck them into this model, and the weights that we learn is a way to define a relationship between all those words and that fish has some relationship with, in the sense that it is in a sentence with these words, and then finally gives us a word embedding that kind of ensures that relationship is in a vector. So yeah, again, just a high level understanding is enough. We just want you guys to know how CBOW works. So yeah, that's CBOW. We have skipgram as well, which is essentially just the opposite of CBOW. It's a little bit more harsh in that sense, where you just pass in one word as your input, which is like in this case it would be fish, and then you would expect the model to spit out all the words that fish would have a relationship with in the vocabulary space. So we pass in this sense, we pass in fish as the input, and we would expect the output to be the grizzly bear goes to the river to catch. And that again is essentially doing what we did in CBOW, but in opposite. But essentially it's the same thing, because you get all these weights that you train as a result of backprop, and you use those weights in your word embedding. And again, that just kind of, I guess you can say, vectorizes the relationship between all these words in the sentence to the word fish. So yeah, two different ways. Each one has their own set of advantages and disadvantages. I'm not too sure which one. This kind of sounds like Google rank search. Yeah, you can think of it like that. See, one predicts a word and the other predicts a sentence. You can think of it like that. Yeah. Yeah. Maybe not a sentence, but a collection of words that relates to the input. Yeah, essentially, this one predicts related words. So it's a little bit more intensive, which is why I believe skipgram is usually preferred when you have these smaller vocabulary spaces. Yeah. I believe, yeah, it's used for smaller vocabulary spaces, and I believe it works better on words that are found less often, the words that occur less frequently. The input OHE. Yes, exactly. When we begin using either skipgram or cbow, all our words are one hot encoded. And the job of these models, cbow and skipgram, are to give us back um, word embeddings which have context to them. So yeah. Yeah. These are just two commonly used models, but again, there are a lot more out there, as it usually is in this field. So definitely go check them out when you guys can. Cool. All right. Yeah, we can move on. So yeah, we're more interested in what we get from these models, these word embeddings. So these word embeddings are going to be these huge vectors. Again, I guess it depends on how big your vocabulary space is. The bigger your vocabulary space, the more values you need in your vector to give these words more context. So yeah, and I think this is actually a really good way to understand what word embeddings really are. They're essentially they're just a bunch of vectors. So let's say you start off with this vector king, all right? It's all represented in colors here because it's easier to visualize in that sense. So you begin with king, and since all these are essentially vectors, all these word embeddings are vectors. King, man, woman, they're all vectors. You can subtract and add them, which is weird, but that's something you can do because they're all vectors. You take king, you can subtract. So okay, like before we subtract man from king, let's take a look at king. What does king encode? What is the context to the word king? Well, king would imply royalty. King would apply, well, it's a male. King would imply someone who's in power. These are sort of things that we automatically think of when we think of the word king. What happens when we subtract man from king? Because again, these are all vectors, you can do that. Subtracting man from king just removes essentially that piece of context from king. So since man encodes for, well, gender, male, subtracting that from king would, and since we talked about it, king means royalty, king means male, king means someone who's in power. Removing the male aspect from king, because we're subtracting man from king, leaves us with a vector, right? Which essentially just says someone who's in power and is royalty. So we've lost the gender context to when we do king minus man. Now, when we add in woman to this, we're adding a new vector. We're giving this subsequent king minus man vector more context, right? And when we think about it, woman encodes for, again, for gender, but for female this time. We added to king minus man, and now we're adding female to royalty and power. And when we do that, we get queen. And this is kind of a good way to like understand what these word embeddings are, what they really mean. And it's actually pretty cool if you think about it. It's kind of how we work, how we think about words. So yeah, it's just a cool way to think about how these work. You take king, subtract man from it, subtract the gender aspect from it, so you just have royalty power, and then you add in woman, and that converts that to queen, gives you the word embedding queen. So yeah. Does anyone have any questions about this? Oh, there's things in. Yeah. So these.
So,
Yeah, go for it.
oh, so I was just wondering, for each of the I guess like indices in the vector, does each one just represent every other word in the set, and then like the weights represent how closely related each one is to each other? Or how is
Yeah,
it actually weighted?
yeah. So again, so these weights are learned when we use our CBOW and skipgram models. So in a sense, we don't really know what they mean, but intuitively, yeah, what it's doing is it's encoding. Um, so it's essentially encoding context for the word. It's giving these words it's giving these words a stronger relationship to some words than to other words. So king, so like if you take the like let's say like this. If you take the vector king, and if you take the vector royalty, and if you find the dot product between these two vectors, you will get some really large value that shows that these two vectors have um, a strong relationship to one another. But taking like the word king and like I don't know, let's say the word grass and do the same thing, you won't get as big of a relationship when you calculate the dot product. So you can just think of these vectors as holding values that um, give these words context in the most general sense. Um, and again, since all these weights are learned, we're not super sure what they really like, what each value in these vector encodes for. But essentially, they're just encoding for how all these different words are related to all these other words in the vocabulary space.
Okay, that makes sense.
Hmm?
So is it the model that ends up deciding how large these vectors are, or is that something like a hyperparameter?
So these, how large these vectors are depends on how big our vocabulary space is.
Got it.
So if you think about it, yeah, a larger vocabulary space, you would need more context because you have so many more words that are giving context to a particular word that you would need a larger vector to hold all that information. So yeah, it depends on what the vocabulary space is, how big that is.
Okay, that makes sense. Thank you so much.
Yeah, no problem. Let's see. I'm still not clear on how the CBOW and skipgram make the vectors for the words. Yeah, we can go back to that super quick. So let's take CBOW for example. CBOW is essentially, so just think about this at a really high level. CBOW takes in um, all these words. So let's say we have this sentence in our training data. The grizzly bear goes to the river to catch fish. Fish is the word, and let's say we stop the sentence there. So we only have the all the way to catch. We don't have fish. We have a blank in space of fish. We want this model to predict what this blank would be, right? And you can assign the blank to any other word in the sentence. You can put the blank bear goes to the river to catch fish, and you could tell the CBOW, hey, I want you to predict what this word is going to be in relation to all these other words in the sentence. Um, so again, let's try to get CBOW to predict the word fish. We pass in all these other words in the sentence. Um, and since this is a neural network, it's a fully connected neural network. It has all these different weights, um, and eventually you get an output that is some prediction for what this blank is going to be. And initially, it is going to be wrong most likely. And that's where backpropagation comes in, where we calculate an error, we backpropagate that error, and we retrain these weights. And eventually, after a while, you get these set of weights that ensure the output is going to be fish. So now what you've done is you've created this model that takes in all these input, which are these words, um, and you get this output, which is another word. So all these input words are the words the to catch, and the output is the word fish. So what you can think of, what we're doing essentially here is, at least intuitively, is we've taken all these words, the all the way to catch, we've calculated some weights, and then finally we get the word fish. So now we've calculated a relationship using all these weights between the words the to catch and fish. Um, yeah. Um, and all these weights that we've trained are is what makes up the word embedding for the word fish. Since Yeah, because fish is related to all the input words, and these weights give us that relationship. Um, so yeah, I hope that answered your question. It's essentially it's the weights that make up the word embeddings, and that's what defines like this sort of relationship between the input words and what the output word, in this case fish, is. So yeah. Um, how did the vector come out of all of this? Um, Actually, the vector is calculated by multiplying the weight matrix that you get with this with the input vector for not the input vector, sorry, but the one hot encoder vector for the word fish, and that essentially gives us like one aspect of the weight matrix, like one row of the weight matrix, which is encoding so again, getting into all this discussion would take a really long time, and we just want to give you guys a high level understanding of all of this. So definitely go check it out online if you guys are interested. But yeah, it's just think of it like this. All the weights from this model is giving us the word embedding for this output word, which is fish. That's honestly, that's the best way to think about it. The most simple way too, for sure. So yeah. Yeah, exactly. Come over to office hours and we will definitely talk about this in more detail. Yeah, let's move on now because we have a lot going on. Um, so yeah, we have, let's talk about the motivation for RNNs. So what we've done so far, we have talked about a few models. And so what do these models have in common? Well, firstly, they're all feed-forward models. All the input data moves in one direction through this model. Um, so no result is ever fed back. No result from one neuron is fed back to another neuron in a previous layer, for example. All the input is non-sequential. So there's no concept of like passing in data one by one. Everything's just fed in all at once into the model. Um, the data is static and the input space is independent of all other elements. So if we want to predict, like let's go back to the MNIST data set, for example. If we want to predict for a particular hand-drawn digit, for example, let's say a 6, predicting for that 6 is not based on what we predicted for the previous input or what the next input is going to be. All the data is independent from each other. All the inputs are independent. Um, so yeah, those are the 3 key things that we've done so far in all our previous models. But let's talk about this. What data would result in non-independence? In what situation where each of our data could have some sort of relation, like all of our input data has some relationship to the previous input data or the next input data. Um, we'll talk about this in a bit. Um, and that is sequential data, essentially, input sequences. In this example, we have a video, for example, and all these frames that we get from these input from this video, they're all related to one another, right? We have the next frame is a slightly different from the previous one, and the next one is slightly different from the previous one, and it keeps going. So all this data is not independent; they're all dependent on each other. They'll have some sort of relationship between each other. Um, so yeah, and that's where RNNs come in, because these are essentially recurrent relations. Every information on the past input does influence the next input that we get, because they're all related, as you can see here in this example here. Like we have a man, I think that's a man, and slowly falling over, I believe. And each one is is dependent on each other, because it's a frame it's a frame from the previous frame, and so on and so on and so on. So yeah, another example of this could be a ball bouncing. Where will the ball bounce next? Well, because we have all these frames from a video, for example, they're all going to be slightly dependent on each other because as the ball bounces, you can kind of see where the ball is going. The ball can't quickly just jump to another part of the frame or the image because we know based on the previous input where the ball is going to be moving. And there are different sorts of sequential data: audio, text, all that sort of stuff. And that's where RNNs are going to come in useful as we talk about it. So yeah, I've taken up a bit of time, so I'm just gonna pass it on quick to who is speaking next. So yeah, go for
Oh,
it.
it's me.
Yeah.
Give me 1 second. All right, can you all see my screen? All right, so let's move on to some of the concepts behind RNNs. All right, so let's actually first compare the structure between feed-forward neural nets and RNNs. So with feed-forward neural nets, we have our input features, we pass them through some hidden layers, and then we get our output. So this is just some standard feed-forward procedures that we all should be familiar with, hopefully. But with RNNs, we not only have our input features, but also the hidden states of the previous time step of our network to keep track of. And then we kind of combine these two pieces of information, we pass them through some hidden layers, and then we get our output. So the paradigm here that RNN uses is using the past to predict the future. So that is kind of apparent when we look at this picture of an RNN here that is unrolled across time. So at a given time step t, we take in some input x of t, and then we're combining that with the hidden state of the previous time step a of t minus 1 to predict our output here, which is represented by y of t. But we also have to pass on the hidden states of the current time step of our network a of t to the next time step. All right, so I'm going to pause here for a second for some questions. I think the next slide definitely would explain this like a little better. So this is kind of a more low-level view of what an RNN actually looks like. So there are 3 sets of weights here, U, V, and W. And then S here is just the hidden states of our network, and X is the input, and O is the output. So I think this picture on the right here shows what the RNN looks like when we unroll it across time. So RNN shares like the same set of weights across all time steps. So this kind of reflects the fact that we're performing essentially the same task at each step, but with like different inputs. So let's say we're doing like some machine translation here. So we're trying to translate a sentence from one language to another. So the underlying task of like translating each word is the same, but then here's a little tweak in that we're also like accounting for the context because we're keeping track of this quantity s sub t minus 1. So that's the hidden state of our network in the last time step. Okay, there's a question. Are the shared parameters the weights and bias? Yeah, pretty much. All right, so yeah, with this really helps because it greatly reduces the total number of weights that we have to learn. So this like really speeds up our training time. And so yeah, the important takeaway is, yeah, once again, the weights are being shared across every time step. So this is more apparent if you look at the picture on the left here, because like there's only like 3 numbers here, so U, V, and W. So the unwrapped visual on the right is like very useful for understanding how like the RNN feed forwards, for example, and like how the architecture works. but the visual on the left is like a lot more accurate in terms of the actual like space constraints of our network. And it also represents the recurrence relations between like different time steps of the network. So yeah, share parameters are like used for like a lot of like architectures that we use nowadays, because it really like saves a lot of memories and also like training time. Okay, I'm gonna pause here for a second to take some questions actually. I think I talked about the last few slides kind of quickly, so.
How do we determine the weightages of the previous, like, or I should say the current state and then the new input?
Oh, like how do you combine them?
Yeah, because I'm assuming there's some sort of weightage there or some sort of factor, maybe like a hyperparameter.
Actually, let me go into this in a little more detail. So at like a given time step t, so like we have our input here, we kind of multiply our input x sub t with the weight u. And then there's also another quantity, which is s sub t minus 1, which represents the hidden states of our network from the previous time step. And then we multiply that with w. So when I say multiply, I mean, what I really mean is like matrix multiplication. And then I think we kind of actually like concatenate them. So we don't, so like, I think there are a lot of like different architectures of RNN, but like, I think for this one, it's just like a really like, it's not an actual model. It's just like, I guess an abstraction of what an RNN looks like. So I guess one way to combine them is just to add them. But like in reality, like what you do is you kind of like concatenate them. So you can think of them as just like two pipes flowing in parallel. And then, so you have to combine them somehow. So there are different operations here to get S sub t. And then in order to get the output, we multiply S sub t here by V to get O sub t. And then when we pass on this hidden state of the current time step to the next, we multiply S sub t with W. So yeah, there are different ways of combining like the input and the hidden state from the previous time steps. So adding is just one way, but like that's really basic. But yeah, we're gonna go into this in more detail when we discuss like LSTM later, because like we actually have an architecture to base this on instead of just like a really high or abstraction of what an RN looks like. Does that answer your question?
Yes,
Okay.
that helps a lot. Thank you.
Yeah, no problem. Okay, so let's talk about some pros and cons of RNN. So the one advantage here is like RNN can process inputs of any length. So this is apparent in this unrolled version, because like we have x sub t minus 1 here, x sub t plus 1. So this can go on like for as long as we need it. So that's why we can process input of any length. And on top of that, like these weights here are shared, so it doesn't really matter if our inputs is longer, because that doesn't really like waste like more memory. So this kind of ties into like the next point here, which is how the model size is not increasing with the size of the input, because like once again the weights are shared across like all time steps. And the computation also takes into account of like historical information. So this kind of relates to like how RNN uses the past to predict the future. So yeah, I think these are all like pretty intuitive. So let's move on to some of the drawbacks that RNN has. So the first one is like the computation can be kind of slow, because like I think, yeah, because the output at each time step is related to the hidden states of the previous time step. So you have to process this like sequentially instead of like in parallel, which is preferable. And like we could for like feed-forward neural nets or even like CNNs. And another problem here is like the RNN actually has a lot of difficulty like accessing information from a long time ago, because like, okay, let's go back to the last slide. Okay, what's going on? So basically at each time step, we're combining like some historical information s sub t minus 1, and then we're sort of like incorporating some new information given by x sub t. So what this essentially does is it dilutes the information from the past with some new information. So it's kind of hard for the RNN to like remember like information from the very first time step, like, or at least like the basic, this like really simple model of an RNN. There are definitely like other architectures that can like resolve this issue. Does this have the vanishing gradient problem? Yes, we're gonna go into that like in just a second. So yeah, vanishing gradient problem will become like very apparent over like large number of time steps, because like in addition to like back propagating through like all the layers in our RNN, we also have to back propagate through time to like, I guess, compute the gradient. So if you have like a really long sequence of like words or text or like audio or frames for video processing, like back propagating is gonna run into this vanishing gradient problem, or actually like it can also run into the exploding gradient problem if a lot of your gradients are larger than 1. But the vanishing gradient problem is definitely like a lot more common. And another thing is the RN cannot actually consider any future input for the current state. So yeah, I think this is kind of like intuitive to understand why this is the case. Okay, before we move on, let's just do this poll here real quick, just to make sure we're all on the same page. Okay, there's another question. Could you produce the output over time to see improved results over time from the initial decision, like running the model when running the model at once? Okay. I actually don't exactly understand what this question is saying, but I'm assuming it's like, so actually like, so this is actually all like one training sample, right? So let's say we're doing like translation once again. So let's go through a more concrete example. So let's say we're translating like a sentence from English to Spanish. So like each X here represents like a word in the sentence. And then O here might represent like the translated output. So this is not necessarily like 1-to-1, but it's close enough that we're just gonna assume it's 1-to-1 for now. So like, yeah, like this whole like sequence of X's is just one training sample. So at the end of the sentence, we kind of want to backpropagate our error all the way to the beginning of the sentence. So that's what time means. But like when we move on to like a different sentence, for example, like, yeah, our network is gonna learn because like we already backpropagated, but like in the same sentence across like different time steps, like the network would not be able to learn just yet until it has processed like the entire input sequence. Hope that makes sense. Okay, let's end the poll here. Share results. All right, so yeah, most of them got it right, because like predicting the next word in a sentence is an example of like sequential data. So yeah, most of you got that, or actually all of you who voted. Okay, we have another question. So time would be like position in the sentence. Yes, exactly. I guess in this case, it's not necessarily like actual time, but like when we process something like a video where it's like frame by frame, then I think time is a more accurate word to use. But yeah, the idea is correct. All right, let's move on. Okay, so we're gonna talk about like a specific problem that RNN has in more detail, and that is short-term memory. So basically, as RNN processes more steps, so that's just like sequential, in terms of sequential input, it has more trouble retaining information from like previous steps, because like at each time step it has to incorporate some new information with like the hidden state. So like information from like the first time step, for example, would be diluted. Another problem here is like vanishing gradient would be a huge problem when we're trying to back propagating through time. And this is like especially a problem when we have like really large input sequences, like when we're doing like, I guess, genome sequencing where the inputs can be like really long. So, oh wait, it's an accident. And so yeah, RNN doesn't learn long range dependencies across like time steps, or at least the vanilla version doesn't, but like we're gonna actually go into a variant of RNN that actually can solve this problem. So let's revisit the vanishing gradient problem. So here are some like pictures of activation functions that we discussed in the past. And so the real issue here is the tan H that is right here, because this is kind of like a bottleneck for this particular architecture of the RNN. So here is a graph of tan H and its derivative. So as you can see, the range of the derivative of tan H is between 0 and 1. So when we're trying to back propagating the error through time, we have this term sigma prime here. That's always going to be less than 1 when we use tan H. So like this value here, which represents the error of our network at a given time step, is going to be like become like smaller and smaller as we back propagate through time. So that's basically why vanishing gradient is an issue for really long like input sequences. So yeah, hopefully you guys understand, get a high level understanding of why vanishing gradient is a problem for RNNs. Okay, I'm gonna pause here to take some more questions if there are any. If not, I'm just gonna pass it to Sudhanshu to talk about LSTM, which is like one of the most popular architecture of RNNs, and it kind of like solves some of the problems that we discussed earlier with vanishing gradients and stuff. Okay.
Okay, can anyone see my screen?
Yeah.
Awesome. Okay, so like Jenson mentioned, right, the problem we have right now is that RNNs can't capture long-range dependencies. And that's kind of an issue. So like that very long sentence, oh, my name is Sudhanshu Agrawal. I'm a second-year undergraduate student at UCLA. I went to Nair today to get a slice of pizza. The RNN is going to get completely lost in the sentence. It's not going to know, Sudhanshu and pizza. It's going to like what just happened. So our objective right now is to kind of capture these long sentences, long dependencies. And that's what LSTMs help us do. So LSTM stands for long short-term memory. So it overcomes this problem that we had before. And it's pretty much the most commonly used RNN architecture because classic RNNs aren't that effective, but LSTMs work very well. And as a quick citation, these slides are adapted from Cola's blog post, which is kind of a really fantastic and a blog post that I think everyone I've talked to ever has read this. So definitely check this out. It's really cool. And we obviously, changed it up as we want to. So this is kind of what a high-level view of an LSTM looks like with all the math inside. And don't be afraid. It looks a little scary, but we're going to break down each of these little parts. So from this slide, I kind of want to point out the differences of LSTMs and go a little bit of notation. So each of these little green boxes represent the different units of the LSTM. So they just take in the inputs at different time steps. Now, in reality, we don't have these 50 different units. It's just one unit, but for simplification purposes, it's nice to think of them as different units. So each of the different units takes in a different input and produces a different output. So Cola over here has decided to call the outputs H. So we have H at time t, H at time t minus 1, H at time t plus 1. Inputs as X, of course, X sub t plus 1, X sub t minus 1. So it's simple, input goes to output. And what the other notation over here is that these little pink circles, they represent different operations. So if you have a pink circle with an X, that represents multiplication. So it takes in this arrow, which is an input, takes in this arrow, which is another input, and multiplies them. This is addition, this is a tan H, this is sigmoid, and this is another tan H. So at a very high level, that's kind of what's going on notation-wise. And the main difference with LSTMs, there are two main differences, let's say. So way back when in RNNs, like 5 minutes ago, what happened is the output at a given time step depends on the input and the previous layer's hidden state. So it was just this output dependent on X and some A. What LSTMs do is they have two values coming out of the previous step. So instead of just one, we have two different values, which are these two different arrows over here. And we'll talk about that in detail, what these two different values are. So the second thing about LSTMs is that they have a bunch of structures called gates. Now, gates kind of control how much to weight the previous state and the new state and all those other things. So all these sigmoids that you see here, the sigmoid here, here, and here, these are the different gates in your LSTM. And there are three different gates that we're going to be talking about. So the way an LSTM works is that you get some information. We go back here. You get some information. You give your input at this current state, and you compute an output. So you have previous, current, which gives some current output. And the way information flows is you first want to decide how much of the previous state do you want to keep. So all this while, we have some state flowing through our LSTM, some memory, long short-term memory. We have some memory that's being preserved inside our LSTM. And we want to decide, hey, at this particular step, how much of that memory do I want to use? How much importance should I give it? And that's what the forget gate does. It decides how much of that memory to keep. Then the next gate is the store gate. It decides, hey, I've just got some new information. How much of that do I want to keep? So it's a balancing act, right? We have our old information, we have some new information. We need to balance them out and decide how much to keep. And that's what the store gate does. Once you forget and once you store, you combine those two in your update step. And that gives you the current cell state. The cell state that you decide, okay, this is what I'm going to base my output off of. And then finally, we take that combined state and pass through some output. So at a very high level, these are different gates that we're going to be exploring in LSTM. Okay. So so this kind of represents the cell state. So this C, I'm not exactly sure what the notation he thought of was, but C, I'm going to call it like the cell state. So C at t minus 1, the previous cell state, gets passed through, does some computation, and will get some new cell state. So that's a very high-level view where the cell state kind of acts like a conveyor belt. You pass in some input, it stays in the memory, it goes through your RNN, you update it, you modify it, use as much as you can, and then you go forward. So yeah, so that's a very high level view. I'm going to explore this in detail next, but does anyone have any questions so far? Any notation or anything else? Will we always have just those 4 gates? Yes, actually we have just 3 gates. So yeah, I should be a little bit clearer. We have a forget gate, a store gate, and an output gate. Update is kind of a combining step. But yeah, in LSTMs, we always have just 3 gates. There are other architectures which have different number of gates, but LSTMs in particular have 3 gates. So it's 3 different sigmoid functions here. Any other questions? Okay, so the first gate we'll explore is the forget gate. So to remind you, our objective, we've got some output. We've got this h sub t minus 1 from our previous step. And we want to decide how much of it do we want to keep. So let's think of this like, suppose we want to do all this neural network stuff. How do we decide how much of something to keep? We apply some kind of weightage. And that's essentially what a gate is. So you could have easily replaced the term gate with, forget weighting or something like that. And it would work just as fine, but gate sounds cooler. So this forget gate essentially weights the previous output. Like that's the main thing you should remember. And it's a very simple way to compute what this gate is. So what we do, we take the output of the previous state, the input of the current step, concatenate them. So this is just literally just concatenation. Take one, put it at the end of the other, and we do a wx plus b transform on it. So this is an operation we've been familiar with, since like kindergarten. We just take some input, wx plus b, and apply a sigmoid function. And that literally computes your forget gate. So again, we take the output of the previous state, input of the current step, concatenate them, do a wx plus b, and apply a sigmoid function. And that computes a forget gate. Okay, so now, again, let's do some thinking here. The sigmoid function outputs something between 0 and 1. Now that's super, super convenient. Why? Because we can just multiply it with that state we were looking at. So if we have a 1 as this forget gate, this ends up being like, hey, I keep this memory completely. I want all of it. If it says 0, it says, forget it. I don't care what happened in the past. Let's just move on, right? So that's essentially what the forget gate does. It's this weightage that's applied to this previous cell state. And I want to note here, this W sub f and B sub f are the trainable parameters. This is what we're learning. We need to decide at every step how much to keep and how much to throw away. So that's what the forget gate computes. Okay, are there any questions about this particular gate? Does this sort of make sense? Yeah, it's a little difficult to gauge because the other gates are very similar. So I want to make sure everyone's good with this gate. Okay. I'm going to assume we're all good. So let's move on to the second gate, which is the store gate. Now, the first things first, right? We're going to compute the store gate. I'm going to call it I sub t. And guess what? We're going to compute it in exactly the same way. We're going to get some weight matrix, take the output of the previous cell, the input of the current cell, and concatenate them, do a wx plus b, apply a sigmoid function. So this, if this looks familiar, that's good because it's exactly the same as last time, except that we've changed what the w and the b are. So using this, we compute our I sub t, which is the store gate. Okay. Now the second thing we want to compute is the C tilde. Now we have some input x sub t. We have the output of the previous cell h. What we're going to do is we're going to take another wx plus b and apply a tan h to this. Now, the purpose of this is it's kind of our candidate value. It's like saying, okay, I want to kind of figure out how this is kind of the weighted input of this current cell. So it's like saying at this current step, how much, what is a good representation of my word? And this is what the C tilde is. It's simply tan H of WX plus B, where X is the output of the previous cell plus input of the current cell. I'm going to repeat this every single time because this is the kind of crux of an RNN, is the output of the previous cell, input of the current cell. Okay. And guess what? We do it exactly the same way again. We simply multiply the candidate value that we just had, C tilde, with the store gate. And again, since store gate is a sigmoid function, it's a value between 0 and 1, and we simply weight it. Okay. Does that make sense? Are there any questions? Everyone seems a little quiet today. Either this is making a lot of sense or absolutely no sense, and you can give me a little indication either way. A little fast. Okay. Okay.
What was the point of doing that final step again? The multiplying the C by the I in like the next slide? Oh, so you just multiply them together so that parts of it stay? Or
Yeah, exactly.
Okay.
So yeah, so the gate is, like I said, just a weightage, and it just decides how much of it to keep, how much of it to throw away.
So how does this one weight the amount that gets stored and the last one weights the amount that forgets?
Okay. I see what you mean. So yeah, maybe the notation is a little confusing then. So, yeah, so you can think of it in two ways, right? So this is a value. Yeah, just to maybe you got it, but just to clarify for everyone else, this is just a value between 0 and 1. And you can think of it as forget, you can think of it as keep. It doesn't really matter, it's one minus the other. It just tells you a weightage of how much to keep or forget. Either way, you can think of it either way.
I see now. Okay.
Okay, cool. Yeah. I see there's a comment, this is a little fast. Does anyone, you want to clarify which bit I should go over again?
I think it's just generally speaking, maybe a little bit slower from now. Like I understood it, it's just sometimes it's a little hard to keep up.
Okay, fair enough. Then let me summarize this again real quick, right? So the basic thing that we're trying to do here is we're taking we have two different inputs. We have the previous cell state and the current input. And we're just deciding how much to weight each of them. The way we weight each of them is through gates. And we have two gates. We have a store gate and we have a forget gate. And those gates act as the weightage. Cool. So then what we do, we have these two different values. All we want to do is combine them. So we simply take those two values that we just computed, the weighted current candidate input and the weighted previous cell state, and add them up. So this, what we want to what we want to keep from here, what we want to add from here, and that forms our current cell state. Okay, so yeah, it's literally just like a weighted average, if you think about it, of the current state and the previous state. Yeah, let me pause again then. Does anyone else have any questions? At this point, we basically have the current cell state C sub t, which is kind of an intermediate value. We're not done yet, but this is a big portion of it. Okay. If there are no questions, then I'm going to move on to the next step. Okay. Yeah. So yes, what I said is that we now have our current cell state C sub t, and this is an intermediate value. What we want to do is use this to compute our final output. So we have combined the previous output with the current input, and we have some cell state C sub t. Now, the next gate that we compute is an output gate. So this is the third sigmoid that we see here. And surprise, surprise, we compute it in exactly the same way once more. We have some weight matrix, we have some bias. We simply do W of this concatenated H and X. We do W, X plus B, apply a sigmoid. And we get our third gate, which is O sub T. Okay, so once we have this third gate, which is our third weighting factor, what we want to do is apply it to the cell state that we just computed, or we just spent the last few slides computing. And this tan H is a little subject to variation. So it could be a tan H, it could be a sigmoid, it could be a nothing, right? It depends on what the problem you're trying to solve is. But for now, let's assume we apply some tan H. We simply apply this tan H to the current cell state and multiply it by our weighting factor. And that finally gives us our output H sub T.
I have a question.
Yeah.
Why do you have to like keep doing that same sigmoid? Is it like the same one, or is there differences between that and like the previous two?
Yeah, so operation-wise it's exactly the same, but if you see, these weight matrices keep changing. So now we have some W sub O and B sub O, whereas let's go back here. Here we had a W sub I and a B sub I. So each of these different gates has their own weight and bias matrix.
I see. Thank you.
Yeah, for sure.
Is each gate different for each, like, is the weight matrix of each gate different for each cell?
No, so that's a good point. Each of these, each of the gates has a different weight matrix, but the different weight matrices are shared across all of the cells. So this cell will have the same weight matrices as the next cell and the previous cell and so forth.
Okay.
Cool. Any other questions? Okay, I think we're good. Okay, so let me then, so over here, what we have now is we've computed our final output. So again, to summarize, we've taken the previous output, the current input, and all we've done in all of these gates, all of these fancy notation, is decide how much to weight them. The way we decide these weights are through these sigmoid functions. And the way we learn our sigmoid functions is by looking at those weights and biases, those W sub O, B sub O, W sub I, B sub I, etc. And that's how we compute our LSTM output. So this is like pretty much the entire summary of what LSTMs do. We have a forget gate, which has WF and BF, and that simply computes this weightage value. Then we have a store gate, which computes another weightage value. Then what we do is we simply combine those inputs and the output of the previous gate using this kind of weighted average, quote unquote. Once we do that, that becomes our brand new cell state. After that, we simply pass that through some output gate. So the name of the game here is kind of gates, right? We have all these different gates which look very, very, very similar. The only difference is these little parameters, W's and B's, that we have to learn. So that kind of becomes our entire problem, is that after all of this, all we need to learn are these W's and these B's. These are the things that we need to backpropagate over, that we need to update, calculate the gradients of. These are our parameters. And yeah, that's kind of how LSTMs work. Does anyone have any questions? Does this sort of make sense? Okay. What are H sub T and C sub T again? So H sub T is the output at the given time step, and C sub T is the cell state. It's the memory at that current. It's basically an intermediate value that we've called C sub T. And of course, it's defined over here. This is how we compute C sub T at a given time step.
real quick for the output gate, could you also explain why there's a multiplication there?
Over here?
Yeah, how can we multiply by the tan H? Or like, how can we take like an input from the conveyor belt and we pull that into the tan H function? Like, why do we need that to process the output?
Sorry, why we have the tan H, or why do we have the C?
Or, I'm not sure why we're combining them, right? Like, because we're taking we've already combined the like output from the previous layer into the cell. So now how come we're taking the like information both from the cell and then borrowing from the previous layer again?
Okay, so we're not borrowing anything from the previous layer. At this point, C sub T is already taken from the previous layer. So now we're kind of done, right? So this cell state, we're just applying some non-linearity to this. Like I said, this function could vary. It could be nothing. It kind of depends on the problem. It's like if you're doing classification or something, you might have a sigmoid function here instead. And this essentially is just an extra set of parameters. I mean, we could definitely argue about whether or not we need this gate at all, but experimentally, what people determined is that having this extra output gate helps learn some more values. So it just adds a little bit of extra information to the output.
Got it. Okay, thank you.
Yeah, for sure. Any other questions? LSTMs are super useful, guys. I mean, that's what everyone used before transformers, and there's a lot of models that still use LSTMs, I'm sure. Okay, so yeah, so C sub T is a matrix, right? Yes. So the exact dimensions will obviously vary depending on what your W is, what your B is, and whatnot. But yeah, in general, it's a matrix. Yeah, that's fine. Yeah, for sure. Any other questions? Yeah, this is like the first time we're doing a little bit of math in this particular workshop, so I want to make sure everyone's good with this. Okay, so let's do a poll. Make sure everyone understands what's happening with the LSTM at a high level. Okay, so yeah, go ahead and answer this, and let's see what everyone's at. Is this essentially asking, how do you compute each of the gates? What values do you take in? And remember, each of the gates is computed in exactly the same way, using exactly the same values. Okay, we're getting there. A couple more people. Because if you understand this, I think you're pretty much set. After that, you can look up the formula anytime you want, but this is kind of the crux of what makes an LSTM. Okay, 10 more seconds. Come on, there are 2 people left. We can do this. Okay, let me end it here and share the results. So yeah, so as all of you got it right, the correct answer is C. So we've taken the previous cells. Let me go back to the slide real quick. Each of the gates, these are exactly the same, is computed using the previous cell's output H and the current cell's input X. And of course, we have some weights and biases that do the heavy lifting, but these are the 2 things that get passed in. Okay. I think there are a couple of other confusions, and I think that maybe we have 1 person each who said A and D. I'm guessing it's mainly because I framed the questions that as a little tricky, but it's good to see that a lot of you got it right. The cell state, remember, is just an intermediate value that keeps getting passed out. And the gates in particular are computed using only the output. The gates in particular. We do use this previous cell state, but not to compute the gate in particular. Okay, any last questions about LSTMs based on what you saw in the poll or anything? Okay, I think we're good. So, Jenson, you want to take it over?
Yeah, sure. Oh, can you all see my screen?
Yep.
Okay, let's move on to talk about some of the applications of RNNs. So RNNs and LSTMs in particular are used extensively in NLP, which is natural language processing, or at least this is the case before transformers are invented. So some example of task in NLP includes speech recognition. So that's basically what Siri does. There's also language translation, which is what Google Translate does. And there's also sentiment analysis. And I guess RNNs are also used in like some time series analysis in finance. Like one example of that would be like predicting stock prices. But like we all know it's not very like accurate after the GME stuff that happened like a few weeks ago. Okay, I thought that was a question. So the current state of the art network in NLP is GPT-3. So there are a lot of parameters. There are 175 billion parameters trained on 45 terabytes of text data. So that's an insane amount of data. But that makes sense because like NLP tasks are like usually really complicated. Like how does a computer even like understand like what humans are saying? So that's actually like a really complex task. So it makes sense that we need like a lot of parameters and training data in order to accomplish that. But the thing with GPT-3 is it actually primarily uses transformers, which actually I think Advanced++ did like an entire workshop on transformers. It's like a really cool topic, but then just a fair warning, there's a lot of math behind transformers. So we're not actually gonna go into it today because as you can tell, we're a little bit short on time. So if you're interested in GPT-3, feel free to check out these articles here that we have included. And yeah, so transformers kind of solves like a lot of the problems with RNNs that LSTM also solves. But the best thing with transformers is it actually can process like sequential, like its input data like in parallel, which is unlike LSTMs and RNNs. So the way it does it, it's like a little bit more involved. So like I think there's an article here like discussing how like transformers are taking over like LSTM and how like LSTMs are kind of dead right now, but I think LSTMs are still like relevant, but like I think for some applications like transformers are definitely like superior, like NLP. So yeah, essentially how transformer works is it makes use of this a mechanism called attention, which is kind of similar to like the gates in LSTM, except like you can parallelize it basically. So there's actually a paper here that is written in 2017. So this is really recent. So I think transformer wasn't like really a thing until like 2018 or even 2019. And then here's an article like that is explaining like how a transformer works and a little bit more like this is more a graphical approach as opposed to just like all math. So these are some resources that you can check out if you're interested in like attention and how transformers work. Okay, we actually prepared some discussion questions here. So I want to open the floor to you guys. So these are kind of like useful like questions to review, like all the information that we discussed in this workshop. I know it's a lot to take in, but yeah, here's the chance to, I guess, review some of the materials that we have covered. And also, if you have any questions, feel free to. Now would be the time to ask them because we are towards the end of our workshop. Okay, so the first question is describe one hot encodings. So I guess the context here is like, let's say we're trying to like, given a sentence, we're trying to predict like the final word. So like how could we represent a word in one hot encoding? Okay, so someone said a giant matrix of zeros with a singular one. So it's actually just a vector, but yeah, I think the idea is right. And I guess the length of the vector would depend on the vocabulary space or that you have, or the number of words in your vocabulary for that problem. All right, the second question is what kind of data are recurrence models most useful for? So some example would be nice. Sequential, yes. Can you guys give some example as well? Audio, video, sentences, text, yep. Correct. So very nice. You guys are remembering like what Adithya is discussing about word embeddings. So I'm actually really impressed. Okay, so the last question is, can you use recurrence with convolutional models? Okay, so I think this question is phrased like kind of in a confusing manner. So I think the question here is like, can you combine like elements of a recurrence model with like a CNN? If so, like, can you give an example of an application where that will be useful? Yeah, good for videos. Yep. So basically, like when you do like video processing, like you divide your video into like frames, and then like basically your network itself would be a CNN for processing, like, because CNNs are good for processing like a frame in your video, and then you kind of combine that with the like maybe like an LSTM architecture where you like feed the last frame into the current frame as well. Tracking objects, yep. Absolutely. All right, so those are all like really good answers. And also thank you for the participation. That was very helpful. We also have some answers here. Which stage do we incorporate RNNs into CNNs? Okay, that's a good question. Let me go back to LSTM slides. So remember, like for our CNN, we have like a number of convolutional layers and max pooling layers. And then at the end, we have some like fully connected layers. So I guess the C sub t here would actually represent, or actually maybe not an LSTM per se, but like the hidden state would be just before we get our output. So like, I think when we get our output, we're applying a softmax function, assuming we're doing like multi-class classification. So the hidden states would be like just before we apply that operation. So is RNN having a time factor distinguishes itself from a CNN? Yes, so like a vanilla CNN doesn't actually like have like a account for time. So it can actually like do like sequential data analysis, but it's actually not too difficult to incorporate the recurrence nature of RNN into like a CNN architecture. But yeah, the CNN model that we talked about in, I think, workshop 3, that doesn't actually like factor in time itself. Okay, so those are good questions. So the last thing that I want to cover is like, so in the next workshop, we're going to start using Conda. So if you haven't installed it yet, then yeah, please make sure you install it. It should only take you like about 20 minutes. So yeah, that's pretty much it. Okay, any last questions that you want to ask? Oh, and we also have like other resources. So these are all like really cool resources. I highly encourage you guys to check them out. And yeah, thank you all for coming. I know this is a very long workshop, so thank you for sticking all the way to the end. So we have our office hours actually right after the workshop. And please also fill out our feedback form here and follow us on Facebook. So yeah, thank you all for coming. I'm gonna stop sharing right now and stop the
Thank you,
recording.
guys.